Zoom?
Yes. Are you ready to start?
Oh, yes, thank you. Yeah. Yes.
Okay. Well then, we are very happy today to have Ross Street from Macquarie University to talk about homodular pseudofunctors as projective invariants. Thank you very much.
You might have to stay over there actually. I don't want to be seen. Oh, actually no. You have to like you have to change. You have to use here. You have to stay here actually.
So what do they actually?
No, you have to stay here because otherwise you cannot change.
Oh, I have to stay.
You need to control the.
So it's just like sorry. Well, thank you for saying that. Okay.
I'll have lunch. I'll have lunch at 1.
Okay. It's already started the meeting. Sorry.
No problem.
There's a bit of chatter around here.
I didn't say to. Big fan.
Okay, well, thank you very much for asking me to give this talk. I'm actually in what a homological country now, not sure.
Well, go there because they were going to see you. I'll change it for you.
Sorry. So anyway, that's just a matter of where the Aboriginal name for this land comes from, but that's actually where my home is in the Turramurrugal country. So can we move to the next slide? Thank you. Oops, yeah, there. So the way this started was I was sort of cleaning up my room and came across some notes of Flavia, notes of my notes on the seminar that Flavia gave in 1985 in Buffalo, and it was somehow he had Joyal's notes, and or this little a preprint perhaps of this particular article, which in the abstract I said it was 8 pages. I realised there are 3 kinds of mathematicians, of course, ones that can count and ones who can't, and there are only 6 pages, but still an important paper, I think, and sort of has gone missing a bit. Can we have the next one? Yeah. So there are 2 techniques in this paper that are sort of split up into 2 research projects, and I wanted to try and get a little bit of both of them in this talk. But I should warn you that they haven't come together to solve this problem that I'm interested in, which is to do something similar to what Joyal does, which is basically for the symmetric groups. In passing from, so there's an old result about the symmetric groups, that the nth symmetric group sits inside the, well, it sits inside the n plus first, but that's not a retraction. But however, if you pass to homology, then that is a retraction. And well, 2 techniques of it. The first technique is to construct a universal homological functor and prove that the retraction property for that holds. And so every other, this takes care of any other possible homological functor that you might want to look at. The homology and cohomology are really just duals of each other. And so this sort of explains that just about any reasonable concept of homology would have this effect of turning this into a retraction. Next one. And the second idea is this business of going from n to n plus 1 reminds you of differentiation of species, or if you haven't done species, of differentiating Taylor series. If you just take the coefficients, the Taylor coefficients, then differentiating a Taylor series just adds 1 to the subscript on the coefficient, and the integration gives the retraction. So I want to acknowledge, well, I've already said that a little bit, that it started up during my visit to Buffalo, but I'd sort of I somehow turned up in my office with the actual conflow article of Joyal, which was published after the seminar, actually. But somehow the first project, the first of these things of mine has gone for more than I was really preparing to do, because Nathaniel has given me a lot of feedback, and so I've tried to push it to a better and better result. So I think it's better than my original version that I put on the archive, thanks to Nathaniel's help. And as I warned you just a little while back, the final goal about the general linear
I hope so. I hope JJ has booked it.
sequence. I haven't really turned it into a. Sorry, I'm getting interruptions here.
Perfect. Yeah, we had the room booked for a workshop.
You have a booked room book.
Yeah,
have the room
every
booked?
Friday at this time.
Oh, I thought JS booked the room.
Well, we've got a problem with the double booking of the room.
JS is out. No. Are you sure you have a workshop here, right?
Yeah, the students waiting online to join.
Well, we have to leave the room, I guess.
Sorry.
I really thought that JS booked the room. I'm so sorry. Zainab, we have a problem with the room. We have to leave and change the room.
It's okay. We'll just check if we can do it out here instead. Sorry, do you mind?
Are you sure about that? I'm really sorry for this.
Yeah, no, that's okay.
It's just that this is going overseas as well, and yeah.
Yeah. You mean it's being broadcast, right?
Yeah, broadcast, right.
So weird, because we've got a link that should be working at the moment too.
Oh.
For this room.
I don't know if that is that weird. I don't know whether
That is weird.
Is
I
it?
don't know how that's.
Sorry. Do you need the room or not?
Are you able to connect from there? We're just seeing if we can connect through a.
Really thank you for
computer to
this and apologies.
Yeah, sorry for.
If you can't, you have the priority, so let us know. Yeah, sorry for that.
Go on to the next slide anyway. So I'll try and describe the first technique. It's to construct this universal homological functor. So he starts with the category of finite groupoids and the category of groupoids where the morphisms are just the discrete vibrations. And you have an additive category, and then he defines a homological functor to be really a pair of functors, one out of groupoids and one out of groupoids with the discrete vibrations, which have these axioms satisfied. And the three really, the first one is that it's really a two functor into a discrete, locally discrete two category A, and there's a Chevrolet-Beck type condition, and also that the A preserves finite coproduct. And the universal homological functor is obtained by some sort of standard two category theory or category theory using the finite coproduct completion. So it's hidden in this construction is the FAM construction for finite coproduct completion. And that gives the universal one. Now, next thing, did we skip? Oh, no, that's fine. Okay, so I'm wanting to do something more objective, I guess, and without dealing with additive categories in the first instance to see, because actually in the paper, not just the FAM construction that appears, but he has to pass to what I call modules, distributors, profunctors, and use them. So I just wanted to remind you what a fibration in bicategory is. It's not quite, it's a sort of pseudo fibration if you're working in a two category, you're only working up to equivalence. And so let's suppose we have a bicategory that admits what I've called comma objects in the past and what is an abstraction of the comma category construction. But I'd rather use the word slice. It's a bit more general than the usual use of the slice over just this particular object, but you can, I'm just using slice for comma categories in general. So if you've got comma categories or slices, then any morphism you have will induce something from, this is really co-tensoring with 2, the slice of E over itself, and that's really the identity of arrow of E over the identity arrow of E. And so you get this thing P bar going from E to the 2 to A over P, and it's induced by these conditions here. And you call the morphism a vibration when this P bar going from here to here has a right adjoint with an invertible co-unit in the bicategory. If you wanted the strict, if you're in a 2 category, you could ask that the invertible co-unit was not just invertible, but was actually an identity, and that'd be the usual notion of vibration. And the pullback of vibration, they're all automatically pseudo pullbacks, and hence bicat. If you're in cat, and hence they're bi-pullbacks as well. So the bicategorical ones. So you can actually, if you're in CAD, you can actually take pullbacks if you're dealing with vibrations. And I'll give you the pseudo ones. But people are not so used to looking at co-vibrations, and unfortunately, as John Gray pointed out, Grothendieck's terminology didn't fit with the topology terminology for what a co-vibration is, and so what Grothendieck calls co-vibrations, we call op vibrations, or zero vibrations, as they got called once by Gray as well. So anyway, the notion of vibration has four joules itself. The joule in K co, which is reversing 2 cells in K, and that's called op vibration. And that's just about, for example, in cat, the opposite of a vibration is an op vibration. And then when you take the opposite of K, then you get the notion of co-vibration. So I've written down what that is. You get, instead of a P bar as we had before, you've got a U bar going into the, now these arrows going up are the co-slice. So co-slices are just the dual, the op type dual of slice. A little bit more, I'll talk a little bit, I think, about how you construct them in the category, in bicategories or enriched categories or something like that. So the one thing about these co-vibrations in VCAD is that each one is equivalent under A as an object under A to the inclusion of a sieve. So a sieve, you probably know from Topos theory, there's a bunch of objects such that anything with an arrow into one of these objects, the domain is also in there. So in particular, every co-vibration in VCAD is a fully faithful V functor. Okay, sorry, we've got to do this. So I've come up with this notion of homodular pseudofunctor. But the main goal was to get a characterization of the process of going from VCAT to VMod. We've had various universal properties, and there's a bit of a history, and Nathaniel has pointed out even more history than I'd remembered, that I have seen most of that in the past, but I had forgotten it at the time. But also, there's very little you need for this universal property. You don't really need each arrow to go to one with a right adjoint, as happens when you're going from VCAT to VMod. You only need the co-vibrations for that to be true. And then you have some kind of Chevalier-Beck condition for by push-out squares like this, where the I is a cofibration. And the I is a cofibration and the J is a co-op vibration. You only need it for that case. And I had more in my first version of this. I had an extra axiom, which turns out not to be necessary, and it's quite good that it's not necessary because it involved limits, and this is all about colimits. The cofibration definition involves co-slices, and this by push-out is a colimit condition too, a bicategorical colimit condition.
Does K also have to be a cofibration in that diagram?
No, well, yes, if this is a by push-out.
Is that must be
Probably, yes, exactly. Yeah, that's a good point. Yeah, please interrupt if you have questions like that. Good questions, okay. What's this about? Oh, yes. Well, if the K does actually have co-slices, you can prove that that actually every morphism does go to one with a right adjoint. And I think I've got a little bit of a proof there, have I? Next. Yeah. So in this diagram, in the definition of the cofibration, the co-slice was the other way around. But if you've got the other one going the other way, then you can always factor an F through a right adjoint of a cofibration together with a co-op vibration like that. And so, yeah, anyway, from that little diagram, you show that this F can be written as, or when you apply T to it, it can be written that way. And of course, pseudofunctors all preserve the junctions. So if you've already got an adjoint, as you have for J, that gets preserved by T. So anyway, both these things have right adjoints, so TF does. Anyway, that's, I don't want to prove too many things, but that was simple enough. And then there are many ways of getting new homodular pseudofunctors from old ones. If you've got, excuse me, if you've got a fully faithful pseudofunctor, meaning that on the HOMs it's an equivalence of categories, then if you compose that with something that's already homodular, you get a homodular functor, and there's an if and only if they're just fully faithful. So that's a way of getting, and we'll use that to get, we'll use that property later. Now what's this one? That's on the other side. So this one was when you post composing. I'm not composing the way Robin does, but thank you. This is the way I put it. This is just as you see where the domains and codomains are. The X is the thing in common. And this way is composing the other way around. So if the S preserves all the stuff that was talked about in the two axioms, then it will take a modular functor to another modular functor. And this is another one. If you've got a modular functor and you hom in, hom means for me the same as Benaboo, pseudofunctors. Sometimes I write it a different way, but it's a good notation people have used before. So those pseudofunctors from A to K, and these are pseudofunctors with lax natural transformations because that's just because when you have an adjoint, you use the naturality, the pseudo-naturality for the adjoint.
Is it true also the opposite? So if something like this is homodular, is also T homodular?
No, no. Well, this in this particular case, or just the opposite of this?
The opposite of the proposition, yeah, the last proposition.
Yeah, at the moment. You've got to be a soft dual concept. Did I bring that bit of water I had? Oh, yeah, there it is. So the main example is just going from categories to modules or to profunctors. Or more generally, you're going from enriched categories to the category of the enriched modules. So those two things are examples. Or the one's particular case of the other. If you hom into this is very much like the what they call them, Grothendieck's
Derivators.
Hmm?
Derivators.
Derivators, thank you. Derivators, yeah, or Heller's homotopy theories. So if you hom into a complete category, then you get a modular functor like this, because you've got the things you need, the adjoints you need, count extensions, and yeah. So also this dual case works. In that case, not for V, because fibrations and co-fibrations have a better relationship in CAT than they do in the co-fibrations of the V CAT, but not so much for fibrations. And then there's this kind of stuff that Rose and Wood looked at, which was other examples. They were looking at other examples where you could create something like what Wood called pro-arrow equivalents by the process of taking two-sided co-modules, discrete two-sided co-modules. And anyway, this example going from topless from toplosses, and geometric morphisms, and this is toplosses and left exact functors between them. So that gives you another example. So the question is, what is the universal? If you're given a K, what is the universal modular functor out of it? How do you construct it? So in Joyal's case, where he was trying to construct the universal homology functor, he only looked at that one example of coming out of groupoids, and I was particularly mainly interested in the case of K being V cat, but it's kind of an interesting question for any K. So you call this universal if it has the obvious property that any other homodular functor out of K factors up to equivalence through a pseudofunctor from M into X. Now, when Wood was looking at pro-arrow equivalence, he made this assumption that they had the same number, that the objects were the same in this example, for example, that these two guys had the same objects. We can prove just from the universality that they're at least essentially subjective on objects. I don't think, since we've been interrupted a bit, I think we better not go through the proof of that. So in the paper with Verity and Scott Johnson and Carboni, started out, here it is. I doubt anybody would recall this, but this paper was about trying to show what properties you needed of a K in order to be able to construct a module.
They mean the other way, right?
Hmm?
The other way, isn't it?
What properties on the K? No, well, properties on the M you kind of had, because they came from my paper on Gaussian characterization of bicategories, of enriched categories. So, yeah. Anyway, so this K, the property, well, this is M. This is what M, the M you end up with when you start with one of these good Ks. We didn't quite get that they had to be the co-vibrations. But that's true, actually, they are. And that was work of Rosebery and Wood. So anyway, these are the properties that you have finite bicategorical co-products, a quasi-object for every monad, and the co-limits in the Hom categories are preserved by composition on both sides. So if you do have this, then you actually have all finite collages. In this paper, Cauchy characterization of enriched categories, I just looked at the small case, but if you look at the argument, it just carries over to give the finite case. So if I'm writing M lower star, even though in the paper we wrote M upper star, because the things that you have here are things which are sort of lower stars. They have right adjoints which are upper stars. So M lower star is the subcategory, sub-bicategory of M, where you restrict the morphisms to those with right adjoints. So an F will have a right adjoint F upper star. And I'm writing this Macquarie type I for the inclusion pseudofunctor. So Nathaniel pointed out the axioms of Rosebery Wood imply that M is a finite cosmos. So they're pro-arrow equivalents which actually allow you to construct the equivalent using co-vibrations can be done with these. This theorem applies to. So instead of, I don't like changing the name much. I'm using the equivalent word, but I'm trying to. It's a little bit different from what Richard Wood had. So I'm talking instead of pro-arrow equipment, I'm calling it modular equipment. For a bicategory consists of a finite cosmos and a pseudo-functor from K into M lower star. So it's a pseudo-functor from K into M, but everything has in the image has a right adjoint. And it's got these three properties. It's essentially surjective on objects, locally fully faithful, and these are very close to what Wood and in some of the papers with Rosebery used too, except they have identity on objects here. Yeah, so there's this phenomenon that I discovered, I guess, in the Cauchy characterization paper that you could, when you took these finite, or any collage, it also had a universal property for the things with right adjoints. But you want that to happen back in K, not just for the things with right adjoint. So in other words, when you take a collage, the co-cone, all those things will have right adjoints, and something out of that co-cone will have a right adjoint if and only when it's composed with those co-projections. Will have right adjoints.
This is a F bicategorical sort of thing. It's sort of like the F category situation, except bicategorical.
Like, yeah, you've got it in a more discrete case, I guess. Oh, locally discrete. Yes. Yeah, so there's a few little theorems. If bicategory emits modular equipment, this is meant to be a T, but it's a funny sort of a T, Macquarie type T. And that T was introduced as the composite of, can we just go back again? I think I got that. Yeah, T is the composite of, so going from K into M lower star and M star into M. So it's just, yeah. So that's the thing that's going to be the equivalent of T. And modular equivalents preserve co-vibrations. Now what's this one about? This is a sort of technical thing. I think we can skip over that. So this is kind of a general thing, just with those axioms about being universal modular, or the being a modular equivalent, are enough to make it the universal modular thing out of K. And I've got a bit of a proof of that. Well, I don't really prove it. It's actually, this is a technical theorem. This is probably the newest thing. And it's basically the same proof I had in the original version, except that I had something called equi-coinverters in there that are not necessary, it turns out. And with a bit of pushing from Nathaniel, that's what I came up with. We'll just say a little bit about that proof. So the proof is much longer than this. This is just the beginning of it. So you do more or less the obvious thing. You've got t from k to x, and before you had this script t from k to m, and you take your m in k and take what's it called, the collage of that single arrow that exists because of it. It's a particular case of co-slice. And so when you apply t to im, it's into the co-fibration. T, it's got a right adjoint, and so you can go back that way. And so you've got this formula for extending t. So that's the main point. Then you've got to check all the fact that it's consistent with that it's the pseudofunctor and all that stuff. Okay, yeah, next. So in particular, this covers quite a fair bit of stuff too. For example, anyway, I should say what it is. If you've got a finite cosmos, the inclusion of the things with right adjoints in M is universal comodular. So if you started with mod here, profunctors, the things with right adjoints, that's actually equivalent to the Cauchy complete, the categories which are Cauchy complete, and all functors between them. So it's kind of, I used to have this old philosophy that all categories were Cauchy complete. The small ones, doesn't really matter if they're not, because you're only really interested in things going out of them. And so if you make it Cauchy complete, you still won't change the functor category, that is domain. And big categories are usually fairly complete, and the minimal condition of completeness is Cauchy completeness. So that example is important that way. And this was the main example I'm interested in when you have VCAT here. So there's a bit of a difference between this here, you see, because if you applied this theorem to V mod, you'd end up with VCAT Cauchy complete, the Cauchy complete V categories. So that's good. Yeah, so there's a more general, but in this particular case, when the domain is VCAT, there's a more general Cauchy, more general Chevrolet-Beck condition that's holds. You can use that universal property of the homodular universal homodular thing to show how both monoidal structures carry over and also coproduct structures carry over. So if you've got the thing you're going into is monoidal out of VCAT, then the T bar that extends it going into X extends to a monoidal. The T bar becomes monoidal too. Yeah. T is strong monoidal, and so this T bar, okay, that's right. It's not just monoidal, but strong monoidal, and this equivalence is monoidal. I was just hesitating there because I thought I'd said that it was only monoidal. It's actually strong monoidal. Okay. oh yeah, this is the co-product one. So if X has the co-products, then so does the C bar. And that's why I don't really need to have the co-product thing in the definition of homodular, the way Joyal had it as part of the homology thing. That sort of comes up as, okay, so this is the second technique. I still got 20 minutes or so, or 10 minutes. So. Yeah, I think I'm going all right, despite that interruption.
I'm not the organizer, so I think it's going to be fine.
Yeah, okay, but that's not too long. So this is a change of topic, really, but although the idea is they're supposed to come together. So I don't know whether people know this calculus of Q numbers and things. It's quite interesting. So there's the sort of discrete stuff, but there's also this relationship to the finite fields. So Q can be anything, but for my purposes, it's the power of a prime, because I'm interested in these finite fields. So this is really the number of things in a projective plane, or projective space. The number of one-dimensional subspaces of Fn, so it's is given by this, which is kind of Joyal way there back when he was talking about this before he published it, the enumerative combinatorics, it was called, species and things, when he was here. And I remember what pointed out that this is really the construction of the, if you think of it objectively, he didn't use that word, the construction of the two different ways of constructing the projective plane. So you can either cut out the zero in n-dimensional space, if you think of Q as being the space, and cut out the zero and take out non-zero multiples, identify non-zero multiples. But that's that formula. And this is the thing of starting with n-1 dimensional space, and then adding n-2 dimensional thing at infinity, and then to that one you have to add an n-3 dimensional thing at infinity, and so on. So these two things have a sort of constructive definition. Anyway, I've said more than I need to about that. Another thing, this is the integer. This is the, if Q is 1, this is just n. Right, so that's the Q integer. The Q factorial is just as what it is, except you're multiplying Q integers together, and there's an objective way of looking at what that is too. And if you want the order of the finite general linear group, this is the group of invertible n by n matrices over the field FQ, field with Q elements. It's got a nice formula. And in our paper that Joyal and I wrote on representations of the finite general linear groups, we use this phi n thing, which is that. And this gives you the order of the finite general linear group, which is also Q minus 1 to the n of the n factorial. And I'm going to give an argument that I prefer now, or at least for what I'm doing now, these factorials to the phi. You can use them because of this fact, that the Q binomial coefficient, which you would think it would define like that, which is by the usual definition, comes out to be the same. So there's all these extra bits cancel in this particular case. So, and this is the binomial coefficient is the thing you use in proving the Leibniz rule for Taylor series. Yeah. No, that's why that's important. So these Q people, have a whole calculus. They have a derivative called the Q derivative of a function. I won't say where the function is, just think of it as Q as a variable, and maybe formal power series or something like that. So this is the Q derivative of f. You should notice that if Q equals 1, there's a bit of a problem, so you avoid that. But there are all sorts of generalizations of this too, where you can actually incorporate the definition of the ordinary derivative of a function as one of them too. This doesn't reduce to that. Now, there's a Q integral, which involves summation. So it's a pretty easy calculation to show that the derivative of the integral is back to where you started and so on. So, but the interesting thing is that the Leibniz formula, the Q-Leibniz formula, is not the usual Leibniz formula for a product. The usual Leibniz formula would not have that little Q in there, which causes me a little bit of a problem. If that Q wasn't there, it'd just be the ordinary Leibniz formula, but the Q is introduced there, or it's an easy calculation to show this from this definition. And you can either put the Q there or put it in there. So it's in the thing you're not differentiating. One of them. So in this paper with André, we had a tensor product, which was inspired by Sandy Green's paper on representations of the finite general linear group. He had a product of the characters, and which was basically this, but it has a more structural look about it because you're actually taking a quotient space, which generally you don't think about much with vector spaces, but that works nicely. Vector spaces, because they always have a complement, you don't think of the quotient. It works much nicer for functoriality and things like that. So this is the definition. And we defined the dimension function. The dimension series using this 5 thing. And the good thing about it was that this tensor product, decategorified, if you like to use that horrible word, to just the product of the two series in the ordinary sense. And what I've changed it from dim to did. The T is meant to indicate Taylor, because now it's kind of a dimension Taylor series. I'm putting in factorial here, the Q factorial, rather than the phi. And that gives you this property that it's not too different from the dim. It's just got this Q minus 1 coming in. And it still, because of that binomial property, working with both phi and the factorial, does means that this is still true. Yeah. So this is, if you look at the Q derivative of a Taylor series in this sense, a Q Taylor series, then it's just adding 1 again to the coefficient. And so in order to make so the tensor product goes to product. So in order for the derivative to go to derivative, this is a way to do it. You can just add a copy of the field. So push it up a bit, and then it works. The dimension, the T dimension, or the Taylor type dimension of M prime is just the Q derivative of the Taylor Q series. Yeah, so these are a few things on the way to it, and I'm not going to actually prove the Leibniz rule, but I just these are the things that are needed on the way. There's a Grassmann, it's a Q species, we're ending in sets here, so it's not a linear representation, just an ordinary set representation of the finite of this. This is the general linear groupoid, so it's the category of finite dimensional vector spaces over FQ with linear isomorphisms, linear bijections. So it's not just one of the general linear groups. We're not cut off at n. So if you've got that would be what you might call a Q species, and then the other representations, the ones that end up in finite vector spaces or something here, over complex numbers or something, they do. Well, I think André used linear species, but that's not particularly good because there are other things like linear orders come in. And so I think maybe vector species or something like that might be better. Anyway, the order of this Grassmannian, the cardinality of this Grassmannian is that. It's the Q binomial coefficient. So you can actually differentiate things that go into set as well. Still use that adding a copy of FQ. And if you do that, then you can prove this identity. That the derivative of the Grassmannian is obtained like this. And so that's actually, this is a much easier thing to prove. That, the n plus, this is just like it is for ordinary numbers, right? The binomial coefficient can be obtained by adding these things, but it's got this extra Q coming in, which leads us to pretty near the end. So each functor into vector spaces determines a new functor, which I'm writing as m dollar, which you do by just take your vector space. This is the vector space over the over FQ, and just treat it as a set here, and take that many copies of. So that, in particular, if it was FNQ, then that'd be Q to the n. So this is the direct. So you modify it by doing that, and you end up with a Leibniz formula like that. So the reason I thought this was a good thing to bring up, as well as the first part about homodular functors, pseudofunctors, is that we've got a lot of people doing differential categories around. In particular, Robin is here at the moment. So do any of their differential categories have a Leibniz rule which has some funny business going on in one of the variables like that? And I think that's it. Yeah, thank you very much.
Thank you very much for the nice talk.
Good timing. Are there any questions? So that's gone away.
What's the phi? Like, how do we think about phi? How do we think about phi?
The phi.
Like in this Q world.
I did have it, didn't I?
Does it have some meaning?
Yeah. No. Yeah. Can we go back to that? Or?
Yes. Where does that mean?
Where phi comes in for. Yeah, that one, the last one. Yeah. So it's not exactly the cardinality of the general linear group, but it's close to it.
But why in what step are you using this phi?
Well, I'm saying that in this paper of ours, we had phi to get a dimension series, and the reason was you wanted to show that the tensor product turned into multiplication of series just to justify the
this to prove this essentially.
Yeah, so that was, but it also has, it doesn't affect this property. Yeah, if you replace it by the usual q factorial, that gives the same property. Yeah, maybe we lost the audience when the interruption came. Do you think? Is there anybody there still?
Yeah. They applauded. They applauded you.
Oh, thank you.
I actually had a question. So in the specific case of cat V and mod V, people look at when we have a pseudofunctor on cat V and what are the conditions so that we can extend it to a pseudo or a lax functor on mod V. And this is typically axiomatized by the...
Oh, I can't hear
Can
too
you
well.
give me 1 second? I'm just trying to like
I think
raise
he's
the
going to turn
volume a
up the
little bit.
sound.
Can you try now?
Is it better now?
Yeah, much better.
Yeah.
Yes.
Okay.
Okay. So in the specific case where we look at lower star from cat V to mod V, people look at when we have a pseudofunctor on cat V, what are the conditions so that we can extend it to a pseudo or a lax functor to mod V. And the results that exist are typically that the pseudofunctor should preserve exact squares. So I was wondering if you can reformulate this in the more general setting of homodular functors. If I have a pseudofunctor on the domain by category, can I axiomatize when I can extend it to a pseudo or lax functor on the codomain by category by its interaction with the homodular functor or pseudofunctor? I remember it.
That wasn't one of the possible
Propositions, right?
propositions back here, was it? But yeah, the examples. Yeah, these two. So which side is it on?
So if we have a pseudofunctor on K,
Right, like this.
and we want to extend it to a pseudo or lax functor on, is it an X or an A, the codomain?
X. Oh, does that make it?
Yeah, so that we have a square basically. So we'll have an endofunctor on X, such that we have a square or a lax square. So I don't think this is
That's not
among
quite-
the examples.
No. But the thing about inducing the tensor product did involve such a square. The
Right.
tensor product. Yeah.
Exactly.
No, it's a bit hard to do it across this format and have this discussion. Yeah. I'm sorry. Whether it works or not. It sounds like something you could do, you could look at.
Okay. Are there any...
Exact
Sorry?
squares are an interesting thing to coming into this, I guess, to the notion of exact square due to Riemann guitar. Yeah.
Yes, I mean, the condition that the mate is an isomorphism is very similar to the special case of, yes, exact squares.
Yes. Well, that comes up in this pointwise property of kind extension.
Yes.
Yeah.
Okay,
So-
thank you very much. Are there any other questions online? Okay, if not, thank you very much again for accepting to give the talk today.
You're welcome. Thank you for asking me.
Thank
You.